Welcome to This Explainer. Today, we're unpacking a massive physical mystery straight from our source material: how density determines object buoyancy. I mean, we interact with liquids every single day, right? Whether we're just washing the dishes, skipping rocks on a pond, or watching a massive cargo ship head out of the harbor, we are actually witnessing an incredible rule of physics in action. We've all seen this phenomenon in one form or another, but what's the actual scientific rule governing it? How do we crack the code? Picture a colossal iceberg weighing thousands of tons happily drifting along the surface of the ocean, but a tiny, lightweight aluminum cube plummets straight to the bottom of a glass of water. So it clearly has nothing to do with the total weight of the object. So what's this secret mechanism actually at play here? Okay, let's dive right into this. The answer is density, which our source simply defines as mass per unit volume. Think of it as a measure of how tightly packed the matter inside an object really is. And the cool thing is, it's a specific, constant value for each material, meaning no matter how much or how little of a certain material you have, its density stays exactly the same. It acts as a unique identifier, literally like a physical fingerprint for any given substance. We can express this with a pretty straightforward equation, where rho, which is the Greek symbol we use for density, equals mass divided by volume. Now, the mass is usually measured in kilograms or grams, while the volume is measured in cubic meters or cubic centimeters. So when you actually do the math, you end up measuring density in kilograms per cubic meter or grams per cubic centimeter. It is just an elegant, simple division problem that reveals the fundamental nature of whatever it is you're holding. And this brilliantly shows how density acts exactly like a fingerprint. Imagine we have a totally unknown object. We measure its mass and find it's 2.41 kilograms. To make our math a little easier, let's just convert that mass from kilograms into grams, giving us 2,410 grams. Next, we check its volume and find it's 125 cubic centimeters. Well, if we divide that 2,410 grams by the 125 cubic centimeter volume, we get exactly 19.3. If we compare that to known values, that 19.3 grams per cubic centimeter perfectly identifies our mystery material as gold. The math literally gives away the material's secret identity. Section 1, the float or sink rule. Once you understand this, you are never going to have to guess what an object will do when it hits the water. So when we pit objects against a liquid, it's really just a simple showdown of their density numbers. A block of aluminum, it sinks straight to the bottom because its density is fundamentally greater than the density of the liquid it's in. On the flip side, a block of cork floats right up on the surface with only a little portion submerged because its density is strictly lesser than the liquid's density. It's an unforgiving physical law based entirely on that single value. But what about the middle ground? What happens when the numbers match up perfectly? Take a look at the ice anomaly. Because its density is perfectly equal to the liquid's density, it floats, but it remains entirely submerged. It just hangs out right there at the surface, not bobbing high above the water like our cork, but not sinking to the floor like the aluminum either. It's just perfectly suspended. Section 2, real-world measurement, finding the numbers. Because, knowing the theory is great, but how do we actually find these properties in the real world so we can run our calculations? Well, for a regular object, something like a perfect cube, the process is incredibly straightforward. First, you just find the mass using an electric balance. Then you grab a standard ruler to measure the physical dimensions, like the sides of the cube. From there, you just calculate the volume mathematically. So for a cube, you just take the length of a side and cube it. Finally, you take your mass, divide it by that volume you just figured out, and boom, you have your density. But wait, that perfect geometry is great for a cube or maybe a cylinder where you can easily measure the height and diameter. But you can't exactly slap a straight ruler on a random, jagged, bumpy stone to mathematically figure out its volume. Real-world objects are messy, and the standard math formulas for perfect shapes just do not apply here. Instead, we use this brilliantly simple technique called the water displacement method. You start by filling up a measuring cylinder with water and reading the initial volume, which we'll call V1. Then you carefully drop your wave stone right into the water. Naturally, the water level rises. You then read the new, higher volume, which is V2. The difference between those two numbers, V2 minus V1, gives you the exact volume of the stone. The space the stone takes up literally pushes the water exactly that same amount up the cylinder. Oh, and a quick pro tip straight from the source material that is absolutely crucial for accurate measurements. When you're reading those volumes on the cylinder, you always want to look at the water level straight on, at a perfect perpendicular angle. More specifically, look at the very bottom of that little curve the water forms. That curve is called the meniscus, and reading it at eye level from the bottom helps you avoid what physicists call parallax error. Now, water displacement is perfect for a heavy stone that sinks, but here is a really fascinating problem for you. How do you use water displacement for a piece of wood or cork that simply refuses to sink? Since its density is less than the liquid, it just floats on top. That means it isn't completely submerged and it won't displace its true full volume of water. You just can't get an accurate V2 reading. The clever solution here is to basically outsmart the cork by tying it to a heavy sinker stone. First, you suspend just the heavy stone on a thread, submerge it into your cylinder, and read that water level. That is your baseline V1. Next, pull it out and tie your cork to the end of that same thread right alongside the stone. Now, lower both of them back in. The heavy stone pulls the buoyant cork completely under the surface, allowing you to read the new combined volume, V2. Just subtract V1 from V2 and you've got the exact volume of your cork. Knowing these precise rules and measurement techniques really completely changes how you look at the physical objects all around you. Seeing exactly how density determines object buoyancy makes it clear that this isn't just an abstract equation, it is a fundamental property dictating how absolutely everything interacts with fluids. Look around you right now. Can you guess whether everyday items are hiding a heavy or light density fingerprint before they take a plunge? So, next time you drop an object in water, I challenge you, can you predict its secret density code before it even hits the surface? Keep observing and definitely keep questioning the physics of the world around you.